First, I'll talk a little bit about just variational Monte Carlo and then get into more details. The example I'm going to mostly use is electron gas, and I'll explain that much later on in the talk, but just to make things simple, and then you'll hear about more complicated examples later in the week. Why do we call it variational Monte Carlo? It's because of the variational theorem. If we assume that we have some trial wave function, we write it as psi, and capital R means the state of the system, that is the electron position. So at least you'll have, if you have n electrons, you'll have 3n coordinates. And you may also have spin variables. Somebody in the break asked me about spin, and I'll talk a little bit about it. So in principle, you could have the spin variables. So that's what I mean here by capital R. I'm sorry I can't show it, but let's see if I could use this mouse. Okay, so that's this, the psi of R and A. Now A are parameters. I won't say what, but they're parameters in the wave function. For example, if you have a Gaussian, that would be the width of the Gaussian. Or if you have an expansion in determinants, those would be the coefficients in your expansion. But for the moment, they're just abstract parameters, and there could be one of them, there could be 1,000 parameters or whatever. This is this ratio right here, and so this is the real Hamiltonian here, and it's sandwiched in between the wave functions, right? You calculate this integral, and you have to normalize it. And variational Monte Carlo, we often work with unnormalized wave functions. You'll see why in a minute. So that's why we don't assume that that denominator is 1. That's okay in Metropolis because Metropolis automatically normalizes things, as we'll see in a minute. So the theorem is that under certain conditions, this ratio is always greater or equal to the ground state energy. And it would be equal to it in the case that your wave function is almost exact, right? You could, that is exact. Of course, that doesn't happen, right? We never have exact trial wave functions except for something like a hydrogen atom or a harmonic oscillator. Now, what are the conditions? The conditions are important. Basically, of course, as I said before, we would like the matrix elements to exist, that is these two integrals, to be finite, and also the variance. It would be nice for the variance to be finite so we could estimate errors, okay? And it has to have the right symmetries, the wave function. If they're fermions, like electrons are, they have to be, has to be a totally antisymmetric wave function. And it has to have the right boundary conditions. If you violate those things, there's actually something I didn't write there, that it's better if the wave functions, for example, are continuous functions, wave functions. And that's the most common way you fail the variational theorem. If you have a discontinuous wave function or discontinuous first derivative, theoretically this condition still applies. However, in practice it doesn't apply because you don't compute the delta functions required by discontinuous wave functions. We're back. Okay. Oh, okay, so this is one of the things I said. If actually the variational energy equals the exact energy, probably you have an exact wave function, but that doesn't usually happen. Now, in a very important quantity that you'll hear over and over this week is the so-called local energy of the trial function. This is a function of the trial wave function and the Hamiltonian. So we apply the Hamiltonian to the trial wave function and we divide by the trial wave function. So the trial wave function is a function in 3n dimensional phase space, right? And so is the local energy. I mean, we parameterize it by the same variables, R and capital A. Now, why is this important? Well, there's a bunch of reasons. What would happen if you put in an exact wave function into this equation? Well, then h psi would equal e psi for an exact wave function, and then the psi's would cancel out, and this thing would be a constant. So you can think about this as like a surface, the local energy surface. If it's perfectly flat, you've solved the Schrodinger equation. It fluctuates, it's not flat, you're measuring the error in the trial wave function. Like if it goes off to infinity, plus infinity or minus infinity, those are problems in your trial wave function. The better wave function you have, the flatter this function is. Now, how do we measure how flat a function is, how constant it is? You look at the variance of the trial wave function, the variance of the local energy. That's what's shown here. Again, I'm sorry it's so small, but you can see it in the printed notes, I guess. But this is the first moment of the Hamiltonian. The variance is the second moment, right? It's h squared about, and now we're measuring the fluctuations about the mean value. The mean value of the local energy is the variational energy. You can write this. This is the variance. Now, let's not get confused. You have the variance of a trial wave function, and we had the variance we talked about before the break of the error estimate. These are related, but they're not the same thing. These are two different variances. We use the same word because they're related. This is the second moment of the local energy. It's defined by this equation, and how did we get from this equation here to that equation? Well, we said, let's sample coordinate space from psi squared. So psi squared is going to be a probability distribution that we talked about last time, sampling. We want to sample psi squared, right? That's the probability. That's the probability of observing coordinates of position r is psi squared. So we want to calculate this matrix element, so we divide by psi squared. So we have a square here, h squared. So we divide by psi squared, and that makes it the local energy squared, right? So you can see this is measuring the second moment of the distribution of the local energy, right? So again, if you had an exact wave function, the local energy would be flat and it would be equal to the variational energy. This would be 0, and so psi squared would be, sigma squared, the variance, would be 0. So this is a very important principle in variational Monte Carlo that says the better the wave function is, the smaller the fluctuations are in the local energy, and eventually your Monte Carlo becomes more and more accurate. That is the efficiency of the Monte Carlo. It's not that it becomes more accurate because you run longer, but every point becomes more accurate. And so this is, anyway, so this is the variance of the wave function. So often there are two things that we use to characterize the wave function: the variational energy and the variance. The variational energy, we can only use this to compare two wave functions. We can say this wave function is 1 millihartree lower in energy than that wave function. But we still don't know how far it is away from the exact energy. But the variance, on the other hand, is an absolute measurement because we know the exact wave function has sigma squared equals 0. Variance is, 1 Hartree squared. That tells you something about how much the local energy fluctuates and how bad the wave function is. Now, here's a slight historical slide. The first major quantum Monte Carlo calculation was the PhD thesis of Bill McMillan, who was a graduate student of John Bardine's at University of Illinois. So Those of you who are graduate, who's a graduate student here? Okay, see, you can do a PhD thesis that gets mentioned in a historical context. Of course, you have to have John Bardeen as your thesis advisor, but but you notice that Bardeen didn't put his name on the paper. Good for him. Anyway, this is what he did. He realized that the classical Monte Carlo and molecular dynamics methods had just been introduced in the previous 10 years. And he realized that you could do interesting quantum things with the same program. You just interpret where classically you have a potential, you interpret that as a wave function, and you do some other things. And it becomes a quantum calculation. And he did, one of our standard tests is helium-4, superfluid helium-4, and he did some interesting calculations on helium-4 involving 108 atoms. Okay, so it's pretty big, like 108 electrons. This 1964, again, this was I think it's almost even before punch cards. And this was generalized by part of my PhD thesis about 12 years later to fermions. This was a boson system. So again, this is a zero temperature or single state method. Now, the nice thing about variational Monte Carlo is this statement here. This is why variational Monte Carlo is important in this context for two different reasons. First of all, you learn a lot about correlations by using variational Monte Carlo. You can use it to learn what's important in a wave function. That is this type of correlation? Okay, it's different than density functional theory. I mean, density functional theory, you can do calculations with different density functionals and you get a bunch of different results, but you don't necessarily know which one's better unless you have an experiment or something, right? In variational Monte Carlo, if wave function A has a lower energy than B, A is better than B. Gives you an inequality, right? It has to be lower by a certain number of error bars, but I told you before, you just run longer if you don't like the error bars. Okay, that's generally true. It's not, I mean, it may be that that if you look at a property other than the energy, B may be better than A for, say, magnetic ordering or something like that. But generally speaking, lower energy means better. And so it's like a signpost that says, go this way. You've made some improvement. On the other hand, if A and B have about the same energy, you've said, well, this correlation is not important in this wave function. That's the first reason why VMC is important. The second reason is that this is the starting place for diffusion Monte Carlo. And so, and generally speaking, the better you do at VMC, the better you're going to do at DMC, right? Now, I think I said most of, then I was saying, the nice thing about Monte Carlo is we're not restricted very much by what we choose for the trial wave function. What do you use in quantum chemistry for trial wave functions? Some of you I know are, what? Gaussians, well, the Gaussians is the basis set. What you use is a Slater determinant. And this is what we call uncorrelated wave function. That is, the only correlation is because of the Pauli principle in a Slater determinant. And I'm going to give you an example of a hydrogen molecule pretty soon. It does not account for an electron-electron correlation. That's the definition of correlation, by the way. And so the rule in Monte Carlo is we can use any wave function we want, subject to, of course, these principles I said already. There's certain things that you have to say. It has to be continuous, proper symmetry, finite variance, normalizable, but otherwise you can do anything you want, except for the efficiency, right? If you have an expansion in 1 million determinants, you may not be able to compute it, right? So, you know, this is where the efficiency measure comes in to judging whether you want to use a given wave function. But there's certain things, like we're going to talk about Slater-Jastrow wave functions. The Slater-Jastrow wave function doesn't take much more time to compute than the Slater determinant, and it has electron correlations built in, and its local energy is a lot flatter. So you make a huge gain in going from a Hartree-Fock wave function to a Slater-Jastrow wave function in efficiency. It's, I don't know, maybe somebody can tell me, it's maybe 1,000 times more efficient to put correlation in the trial function. And the same with more improved wave functions. You gain a lot. And so the idea is to put things in the wave function that lower the energy and the variance and don't take a lot of computer time. So basically, this is kind of the scheme. We sample the coordinates from psi squared using the metropolis procedure I already talked about. We take the average value of the local energy. We then, in these kind of meta steps, then we try to optimize the wave function to get the best upper bound that we can. That's, you know, we had these parameters and we try to optimize. And I'll talk a tiny bit about that, but Miguel is going to talk about that a lot more tomorrow. And, you know, the result is that the energy is second order in the errors in the wave function. Now, I wrote down this formula for the local energy. Again, this is something that's going to occur over and over again. And I wrote it down for generally complex wave functions, so you have just the real part of the local energy that comes in, right? Because usually when you have like systems without magnetic fields, you can just deal with the real part of wave functions. Better wave functions means lower variance. I'll show you this a little. And this is an important difference with classical Monte Carlo. Classical Monte Carlo, if you look at results, you don't often see things more accurate than 3 decimal places. But we can easily compute things to 4 or 5 decimal places accuracy because of this zero variance principle. What is it again? As the wave function approaches the exact wave function, the energy gets lower, the variance gets lower. And so we're in a situation where we win 2 ways. So I showed this already. There's not a whole lot of difference with what I showed before, except the difference is instead of having a potential, I say we're going to calculate the square of the wave function. That's psi 2. Okay, so basically we initialize the state of the electrons, and then we sample, and we calculate the new wave function, or the square of the wave function. We look at the backward probability. We calculate the acceptance ratio. It's the difference in the square of the ratio of the square of the wave functions and the transition probabilities. And then again, if we accept or reject. Okay, it's the same idea. We calculate averages. Of course, we're going to talk about the kind of averages you might want to compute. Now, there's one thing which is kind of an introduction to tomorrow. Previously, when I talked about the transition probability, this is about the question of this sampling function. How do you sample the new coordinates? Okay, what is conventionally done, and I believe this is done in QMCPACK, is to sample from a Gaussian distribution. We could just move the particles uniformly in a box, okay? But we don't do that. We sample from this function here. And this, in the classical literature, this is called smart Monte Carlo. Why do we do this? I mean, there's 2 reasons why we do this. One is a practical and one is a theoretical reason to sample from this Gaussian distribution. We don't have to do this. This is a choice. That is to say, you could do like Macmillan did, just sample uniformly. That would be perfectly okay within variational Monte Carlo. Does anybody know why we sample from a Gaussian? Some people must have some QMC experience. Yeah?
Is that because the old coordinates to new coordinates or the new coordinates to the old coordinates, the consistent probability is the same?
It's not the same.
It's not the same.
That's part of the answer, but it's the wrong direction. If we're doing a solid state system, silicon, a metal, whatever, where we're trying to model an infinite system, we always use periodic boundary conditions. If you're doing a molecule, you put a molecule and you have a vacuum, that's fine. Why do we use periodic boundary conditions? It's because by doing that, you get rid of almost all of the finite size effects. If you try to model, say, silicon with a little silicon cluster of 100 atoms, if you actually look at that, you'll find that every atom is on the surface. So you're not modeling bulk silicon, you're modeling a cluster of silicon, which is physically very, very different. And by putting them in periodic boundary conditions, this means, well, I think everybody probably hopefully knows what periodic boundary conditions are, that you don't have any boundaries. You have effects, you have finite size effects, and there's going to be a lecture about that later on. But it gets rid of almost all of the finite size effects if you want to if you want to be modeling a bulk system. Okay, so in the code, you have to calculate what's called the minimum image, which is basically when you calculate the distance between two electrons, you look at the images in the periodic boundary conditions and you find the minimum one. And that's what you use in your wave functions. And in the potential, you have to do something called the evolved potential because one over R interaction decays so slowly, you have to use special techniques. These are well-known techniques, right? And the code does them. So we're going to learn about that later on. This slide gives you some ideas of how you might select a trial wave function. I mean, the fact is that most of the time, there's only one choice. It's called Slater-Jastrow wave function. But I thought I'd give you some theoretical background on this, right? Okay, I told you already about formal requirements, that you need things like this. In order to play the game, you can't violate these things. I mean, we like to think of Variational Monte Carlo as being exact, that we don't like to make approximations that are not necessary. So we want to always have these things, right? Now, so the first approach is to take a wave function from a mean field theory, for example, a Slater determinant. So that's where you start from. That satisfies these requirements. But of course, if you're going to do that, then you would just use quantum chemistry. This is a Hartree-Fock, and there are Hartree-Fock calculations, either from a molecule or a solid. But this is where you start thinking about what to use for the trial function. Now, the next thing that you might think is you want to expand in basis sets, for example, multi-determinants. And this is what in chemistry is called configuration interaction. Now, for years, we never did this because, why? Why? Only recently have we started doing this. Why don't we do an expansion in determinants like they do in CI? Well, for one thing, the basic reason is that this expansion converges extremely slowly by itself. And it's not what they call size consistent. That is, suppose you have one water molecule and you have to have 1,000 determinants. If you have two water molecules, how many determinants do you need? You need 1,000 squared, 1,000,000 determinants. If you have three water molecules, you need 10 to the 9th determinants. So it doesn't do the kind of problems that we want to do. And so we don't do that. But recently, we've started doing that because we found faster methods. And Miguel is going to talk about this too, expanded basis sets. Now, there's two general approaches to thinking about wave functions that I want to present. They're kind of related to each other. There's the local energy argument and the so-called Feynman-Kacs formula. The local energy argument, I told you what the local energy is. I told you it represents the error in the trial wave function. So the idea is to use that to improve your trial wave function. right? And there's two particular examples. I'll mainly talk about this one, the so-called cusp condition. What happens when two electrons get close together? Or what happens when an electron goes into a nucleus, into an ion? Well, the potential energy goes like 1 over r. It diverges either to plus infinity or minus infinity. So that's a bad place in the local energy where it's going. So you might imagine your variance of your wave function would be blow up there, right? If it goes like 1 over r. Okay, so how do you fix that? Well, you fix it in a very simple way by so-called Jastrow wave function. The other, I'm going to show you this in a minute. The other thing is the behavior at large r. What happens when two electrons get very far apart? And you can show that with a local energy argument, how to fix this. And this leads to what are called plasmons in metals or the van der Waals interaction for molecules that are separated. And these are related to something I'm going to talk about right now, which is the Feynman-Kacs formula. This gives you a connection with the local energy and the wave function. And it gives you a systematic way of thinking about wave functions. So this is an exact formula, which we'll actually prove tomorrow morning. But it has to do with diffusion Monte Carlo. But it says this is the trial wave function, and this is the exact wave function. It says there's an exact connection between any trial wave function and the exact wave function in terms of this is the local energy of the trial wave function. It says if you want to calculate the exact wave function at a point r0, this is the point r0, you start out random walks from r0. This is a random walk. And you calculate this quantity, which is the integral, which is the exponential of the integral of the local energy along this random walk. And then you average over all possible random walks. Now, this is the math, and the random walk has to go from time 0 to time infinity. That is, it has to be a long random walk. Normally, of course, you cannot carry this out mathematically, this average operation. But it's useful that there is this connection between the local energy and the exact wave function. So you can use it to get insight into how a wave function should behave. By the way, this equation says this is like the smart Monte Carlo where the random walk has to be biased by this gradient of the trial wave function. At this point, you can make an approximation onto that exact formula, which is called the Cumulant Approximation, which is quite standard in kind of statistical physics, which says, but actually we're making this for the non-interacting wave function. Remember I said, let's start out with like a Hartree wave function for the trial wave function. And then the local energy is the electron-electron interaction. And this would say that the exact wave function is equal to the exponential. The cumulant approximation means that you take this averaging operation up into the exponent. That's what we mean by cumulant approximation. We take this average up to the exponent, and we say the exact wave function can be written in this form. We write it as e to the minus u, just because we want to identify this part as u. And we say, now, if we're working with non-interacting wave functions, this is the potential energy. So we basically start out at a point and we take the average electron-electron interaction. And what does this averaging do? The averaging essentially smooths out the potential energy. So the U function here is like a potential energy, but it's smoothed out. In fact, there's a certain, you can do this mathematically at this point once you make this approximation, and you can find that the potential energy is the sum over all electron-electron interactions. And once we made the cumulative approximation, we can see that the exact wave function should be a sum of pair terms, because this is a pair term, so this has to be a pair term too. And so that's where we end up with the so-called Jastrow wave function. So the wave function would end up in this form, where U is like a potential. Except it's smoothed out. The 1/over interaction gets smoothed out. And here is where we can now use this local energy argument. That argument sort of suggested that we should get a pair interaction here. Now we can compute the local energy of this. We can regard the U as just a variational function. And what property should it have? Well, one of the things is that we don't want the wave function to diverge anywhere. And so we can compute the local energy of this form. Here, I'm not worried about the antisymmetry. I'm just doing, say, 2 electrons that you don't have to be antisymmetric for. And so the local energy now can be, if you take this as the wave function, this is the form of the local energy. What are the terms we have here? We have the potential energy. This is the bare potential energy. And then we have these 2 kinetic energy terms. Why do we have 2 of them? Well, it's because we wrote this as an exponential. And so when you take a second derivative, del squared of an exponential, you end up with 2 terms. We have del squared of U, and then we have del U squared, basically. This is what I called F previously, is the quantum force. This is del squared U. Now, these 2 terms are pair terms, while this is like a force squared term. Now, the local energy argument says, now, let Rij goes to 0. What terms are going to diverge? Well, we know V of R diverges. It goes like 1/R. And if U function, you can write it as R goes to 0 in terms the derivative at R equals 0. And again, I'm sorry this came out so faint, but basically there is U double prime of 0. That doesn't diverge as 1/R. You have 2/R times the derivative of U. That diverges. And then you have U prime of 0 squared. That doesn't diverge. So you can see that the 2 terms that diverge are these 2 terms. So they must cancel out. So that leads to this equation that the derivative of U at the origin has to equal -1/2 in order for the local energy to not diverge at R equals 0. So this is the so-called cusp condition. And of course, it was known back in the 1930s, but as usual, it gets established. It gets the name of the Cato cusp condition after the 20th person that wrote it down. So who was a mathematician that proved, that this has to be true. And it's true when any 2 charges, that is, particles that interact with a 1/R potential, get close together, there's a cusp condition. You can write down how the wave function must behave. And it must go like a certain derivative. It doesn't matter if there are 2 electrons going or an electron that's going into an ion. There's a cusp condition.
Question?
Yeah?
How did you get that expansion?
This one?
Yes.
Well, I took this and I said, what happens as 2 particles get really close together? Okay, this is 1/R. And that's this term. I'm sorry, instead of saying this equals 0, I pulled this over. I pulled these to the other side of the equation. So there should have been I could have made it simpler. Okay, but this one. Now this term right here, you have to remember in 3 dimensions, what is del squared acting on a function? As I remember, let's see. Del squared of U is equal to U double prime plus 2/R U prime. I wanted to say something else about a hydrogen molecule and about Fermi statistics. The 2 electron, we often refer to a bosonic-like systems, even if they're 2 electrons. And this is the reason. Assume that we have, the total wave function is antisymmetric if we have 2 electrons, and we assume the spin function is a singlet like this. that means the spatial wave function is symmetric, and that's why we call it bosonic, right? Now, if the ground state is non-degenerate, which is usually the case because it's true if the space is connected. Where would be a case if it wasn't connected? If you have two hydrogen atoms infinitely far apart, that would not be ergodic because there's no way the electrons can get from one atom to another atom. But if the atoms are a finite distance apart, then it's ergodic, and we can assume that this wave function is real, positive, and symmetric by fixing the gauge. Otherwise, we could always lower the energy. So therefore, we can always write two-electron wave function in this form, where this is a symmetric function of R1 and R2. Here is the simplest case of a hydrogen molecule. So A and B are two protons, and I just put one electron here, the star. So you have this distance and that distance. And okay, so the restricted Hartree-Fock wave function, you would write it as a product of orbitals for the two electrons, R1 and R2. And you could write down the orbital approximately as an orbital on the A proton and an orbital on the B proton. Okay, so this would be a restricted, so-called restricted Hartree-Fock wave function of that form in the simplest case. Now, the so-called Heitler-London wave function says there's a much better wave function by putting in correlation where you take this product, that is, you put electron A on electron 1 on atom A or an electron 2 on atom B plus the symmetrical combination. A correlated wave function then would have one of these wave functions, which expresses the symmetry and binds the electrons together, times the Jastrow factor. This would take into account the electron-electron correlation. And the cusp condition that I just derived would say this U function has to have this behavior at small r. There's some constant. The constant doesn't matter because that's a normalization constant. You know, if you multiply this wave function by a constant, that's equivalent to putting a U0 in there. And then it has to have this behavior as the two electrons get together. The correlation energy of this restricted Hartree-Fock is 1 eV, 10,000 degrees. Very large correlation energy in the hydrogen molecule. If you use just this simple function right here, you get 95% of the correlation energy by just adding this one term. So that's the advantage. That's always been the hope of variational Monte Carlo. You add this one term to the wave function, and you get 90% of the correlation energy right off the bat. It's not an exact solution, but it's much better, right? Now, back to fermions. This is the kind of wave function they use for fermions. Well, I was doing a uniform system. You have some sort of orbitals that have some momentum, and you just take like an LDA or a Hartree-Fock wave function, and you add in the Slater-Jastrow wave function, the Jastrow function. Now, the new features are that we have to compute the derivatives of a determinant and sample the determinant. And there we use tricks from linear algebra. And somebody asked me about, there's something called the Sherman-Woodbury-Morrison formula that says we're moving electrons one at a time, and we have to calculate this determinant in order to accept or reject the moves. And to compute a determinant is n-cubed operations, right? If you use a standard linear algebra package, it's n-cubed operations. However, if you change one column of a matrix, then you can update the determinant in n-squared operations. And that's what we do. And this is the formula, basically. But I won't go into details, but you can read about it. Basically, you have to keep the inverse matrix in memory, when you initialize the random walk, you calculate the Slater determinant, Slater matrix, you calculate the inverse Slater matrix and the determinant, and then as you're moving the electrons one at a time, the operation is you replace one column because this matrix, this Slater matrix, you know, the rows would be the orbitals and the columns would be the electrons. So you're changing one column, and you have to update. If you accept the move, you have to update the inverse. But that's an n-squared operation. So you save a factor of n by doing these update formulas. So that's why I say reduces the complexity to n-squared for one accepted move. By the time you've moved all the electrons, it goes back to n-cubed. But that means that you can move electrons one at a time without paying any cost. Now, somebody asked me this question about spin. How do we treat spin? Well, mostly we kind of ignore it. First of all, we're normally not worrying about magnetic fields. If you have a magnetic field in your problem, you may have, and you want to consider orbital, not just the Zeeman energy, but the full interaction of the velocity with a magnetic field. It's more complicated. You can do it, but normally, I think in this week, we'll mostly not worry about magnetic field so much. So we usually use we assume that the spins have definite values of Sz, and so we could say we have a fixed number of up and down electrons, and we antisymmetrize only amongst electrons with the same spin. So that would mean that we have a Slater determinant for up spins and a Slater determinant for down spins. For a given Trout function, if a real part of the wave function is also a Trout function, and for example, suppose we had this plane wave, and if we wanted to represent an electron momentum k, we would have this wave function and this wave function for the electron momentum minus k. But normally, what's often done is we just take the real part of these two functions, so that we could have a wave function which was cosine kr and sine kr. And that way, you don't have to deal with complex wave functions. However, there may be reasons why you want to do this. Like when you do that, like these wave functions had definite momentum, whereas these are not. These are mixtures of these. Momentum is. Don't have a good value of momentum, right? They're mixtures of waves going on opposite directions. So for small molecules, you may want to work with wave functions that have all the symmetries of the Hamiltonian. But once you get to a large system, an extended system like bulk silicon or whatever, you're usually happy to ignore those because those quantum numbers don't usually enter in very much. So anyway, this is more of a specialized topic that I'm not sure we're going to get to, but in your problem, it may be important. There's no problem in variational Monte Carlo with dealing with complex wave functions, I should add. You know, the arithmetic on these guys may be, 20 or 30 or 40% slower than on those guys, that's all. Here is the Jastrow. I'm going to talk about a homogeneous electron gas. I guess I only got 10 minutes left, but I introduced a function u of r. That is, this is the determine the wave function that depends on the interaction between two electrons. And we usually split it up into a short-range part and a long-range part, which we expand in the periodic boundary conditions into a plane wave expansion like that. And then we consider these as variational parameters. And this is how we make it unique, is by we say the short-range part has to vanish at the edge of the box. And this is required by the fact that the wave function and its derivatives have to be continuous in the periodic boundary conditions. So we'd have a condition like this. We have the cusp condition. This has to be a smooth function, and so we can expand it in a polynomial basis, and that would be a so-called spline function. A spline is a polynomial where you, say you have a spline in 0 to a and another polynomial in a to 2a and so forth, you require there to be the function to be continuous and with a continuous derivative, and that's what's called a spline. And then you have your variational parameters are the value of the u at the so-called knot values where they intersect. And so this is the total number of unknowns. And those become your variational parameters. That's how you can specify an arbitrary function here, right? And then you could try to optimize that. And then, as I alluded to earlier, this function u of r is actually a long-range function. If you want to have van der Waals interaction, or if you want to have plasmons, this has to decay very slowly at small r. So that you treat it by this plane wave part, and these become variational parameters. And this is what Macmillan did. This is a plot from his paper. And this is what I did for many years too. This is some variational parameter, and this is the total energy here. So you do a bunch of runs at different values of the parameter, and you draw a smooth curve, and you find the minimum. And this is there were two parameters actually. One was an exponent, and one was a continuous parameter. And so you have a different curve for each exponent, and you can see that this exponent seems to have the lowest energy, right? And so this is what you would take as your best upper bound right here, right? And so you had to do a bunch of different calculation with variational Monte Carlo, fit it to a smooth curve, and then analytically find where the minimum is. Now the trouble is, obviously, you have to do, this only works for like 2 or 3 parameters, because otherwise the space is too big. Now what you can do is a little bit better than that, is what's called reweighting. And here is the variational theorem again. This is variational energy. You sample according to some probability distribution, P of r, and then you write these two integrals as integrals over P of r, your sampling function. And you get these so-called weight factors, which is the wave function squared divided by P. And this is the local energy here, h psi over psi. This is just this rewritten to get this. And then this is the sum over your sampled points, which for some reason it says k instead of I, but it should be I. So this is the sampled points. And the limit where you have a lot of sampling, then this becomes exact. Now, having written this expression here, you can just give it to an optimizing out of your favorite library, something that minimizes the energy as a function of A. Because now we have a smooth function, and it can just go do steepest descents and find the optimal value of A. So this procedure we used for many years for about 10 or 15 parameters. But once you get even more parameters in your wave function, thousands of parameters, then it turns out that you cannot go very far in parameter space before the noise kills you. Duodynamics in both R space and A space simultaneously to find the optimal parameters, the optimal wave function. And you can do thousands of parameters, and there's tricks to make it more stable. I wanted to mention, you really should be looking at more things than the energy in variational Monte Carlo. And the simplest thing is the pair correlation function, and its Fourier transform, the structure factor. This is the definition of the pair correlation function. This is the two-body density-density operator. It just simply says, well, the simplest thing is the electron density to look at. The next thing, which is correct in Hartree-Fock, but the pair correlation function, of course, is incorrect in Hartree-Fock because they're uncorrelated. So that's the probability of 2 electrons being a distance r apart. So here's kind of a picture of up and down spins. If you have a spin here at the origin, or electron at the origin, what is the probability of another electron being a distance r away? Once you compute this g of r, that determines most of the other properties like the potential energy, the pressure, and so forth. But mainly, it gives you a lot more information than just the energy. For example, here is in the electron gas, if you just have electrons, here is the pair correlation function for all electrons, and this would be for like electrons. And you see some features. For example, for a Hartree-Fock wave function, this would come in and go to a half here. So this shows you the effect of correlations for electrons nearby. The structure factor is what is measured over here at this giant light source, which is a half a mile away, right? They scatter X-rays off the systems. They measure the Fourier transform of the pair correlation function, which is given by the structure factor. Of course, they do dynamical properties too. This is what you can compare directly with the experiment. Actually, more easily than you compare the energy. You compare the structure factor. It can be used to see the state of the system, if there's some order in it. Here is the structure factor for the electron gas. Here is the Monte Carlo structure factor, these X's, and this red line is the Hartree-Fock structure factor, which is very similar, but particularly you note there's a difference at long wavelength or low K, because you have plasmons in the real electron gas, and in Hartree-Fock you don't. So this is the sort of thing you can calculate, and you can calculate, for example, like what's the plasmon dispersion in your system with variational Monte Carlo by looking at the low K structure factor. Here's the momentum distribution. I won't say how you calculate this. Macmillan actually calculate this, but this is again is the electron gas, and it shows this is the step at the Fermi surface. So you can actually measure this with again with X-ray scattering, but this jump is called the quasi-particle strength, and this shows as a function of density in the electron gas how much correlation is affecting the quasi-particle properties. And so again, this tells you a lot more than the energy. So you have to calculate this integral with variational Monte Carlo to do that. And this shows you that we can get the step here. It's not so easy, but it's possible to get it. Remember I said the two things that characterize a trial wave function are the variational energy and the variance. This is the variance of the local energy. How much does the local energy fluctuate from one point in phase space to another? And what I have here in these yellow dots, you see 4 squares, yellow squares. Those are 4 different trial wave functions. If I plotted Hartree-Fock, it would be up on the 3rd floor in terms of the energy and the variance. It would be way up there. Here is Slater-Jastrow. This is the energy and this is the variance. Here is a somewhat better trial wave function, which involves so-called backflow. And you see that both the energy and the variance came down. Also, you see that generally speaking, these points lie on a fixed line. That gives us an idea of where the exact answer is, which is down here. These are the diffusion Monte Carlo answers, and you see that indeed this line seems to connect up. So this gives us some idea of where the exact energy is. We know the exact variance is 0, but the exact energy. This is not rigorous mathematics, but it does give you at least a pretty good idea of where the exact answer could be. There are different ways of doing this. And it shows, you can improve the wave function in a systematic way. These other wave functions I didn't have time to explain come out of that Feynman-Kacs formula, which I did explain, but I didn't explain how you get these wave functions. But hopefully we'll have a chance later in the week to talk about this. So here's a kind of a summary. This is the error, the logarithm of the error, and this is the logarithm of the computer time. If you take a simple wave function, it converges like 1 over the square root of computer time, and then it flattens out because your trial wave function is not very good, and it's above the exact energy. If you take a better trial function, it converges, it has a better efficiency, so this is smaller, and also goes asymptotically to a lower energy. Now we want to get into here, which is what diffusion Monte Carlo is going to get into, what you really need for applications. The variational method is very powerful since you can use any trial wave function. The scaling, the computational effort versus size, is almost classical, so it's like n cubed or n squared effort. So you can do 1,000 electrons if you want. You can learn directly about what works in wave functions. You have no sign problem that we'll talk about next time. However, the optimization can be somewhat time-consuming. The energy is insensitive to order parameters. Namely, if you're trying to decide whether the system is magnetic or non-magnetic, the energy may be a kind of a hard way of seeing that. Non-energetic properties are much less accurate than the energy. It's difficult to find out how accurate you are. And something that people often don't realize is that the variational method favors simple states over complicated states. Because you can write down a wave function for a simple state easily, but a variational state requires a lot more effort. And so there's a bias over getting a simple answer. For example, I said a localized state versus a delocalized state, or a polarized state over an unpolarized state. There's a bias. We need a more automatic method. The other comment here is what you put into the wave function comes out. That is, if you don't try, for example, if you just try, say, a localized state, you're not going to get a delocalized state to come out of the calculation. So you call this, in computer jargon, you used to call it GIGO, garbage in, garbage out, right? If you don't put in the right type of trial function, you're not going to get it to come out. The more automatic methods have at least a possibility of getting things out that you didn't put in. So I'll stop there since it's noon and we have to eat lunch quickly, and we'll resume tomorrow, I guess.